After studying this module, you shall be able to analyze how decision makers take decisions under uncertain situations, learn what is lottery and about both compound lottery and reduced lottery, learn what is the expected utility theorem and how it works, understand when a person is called a risk lover or risk averse or risk neutral. In general, all the decisions made by a firm or an individual are assumed to be taken under a certain known situation. An individual must have knowledge of his own budget and utility before he can maximize satisfaction. A firm knows what input mix is required to maximize its fixed output. But what happens when there is an uncertain situation? How can a firm or an individual make choices under uncertain situation? This is a big question. There are lots of uncertain situations where decision making is not easy. Firms are uncertain about their output. Example, bad weather can affect their output. Machines can break down. Often, market conditions are also unpredictable. Consumers may not be able to decide whether or not to make a purchase decision when they face uncertainty regarding their income or about future prospects. Every individual behaves differently in uncertain and risky situations. Some people try to avoid risk while some love it. A risk-averse person tries to reduce its risk by adopting certain strategies like purchasing insurance via a diversified portfolio of financial investments and so on. This module will provide insights into about how agents, individual consumers or firms behave in an uncertain situation and what differentiates a risk lover from a risk-averse entity. Now we will discuss upon lottery. Suppose there are n states, 1 till n, and the probability attached with each state is Pi, where I is equal to 1 till n. We have Pi greater or equal to 0 and summation from 1 to n Pi is equal to 1, satisfying the basic axioms of probability. Let xi, where I is equal to 1 till n, represent a price received when a particular state 1 till n has occurred. Then the expected value of the payoff received or lottery is denoted as L is equal to summation, where it ranges from 1 to n Pi into xi. It may also be expressed as P1 till Pn, where the P1 represents the probability associated with the price xi. The prices which an individual receives may be in cash or kind. For example, if there are two states x and y which occur with probability P1 and P2 respectively, then the lottery is denoted as P1x plus P2y. A lottery can be graphically presented as a tree-like structure as follows, where lottery is equal to P1 into x1 plus P2 into x2 plus P3 into x3. We can also represent the lottery as a vector in a probability simplex, that is a vector of probabilities. Suppose a lottery is represented by a vector of probabilities given by P star is equal to half, half, 0, where P1 is equal to half is the probability of outcome x1, P2 is equal to half is the probability of outcome x2, and finally P3 is equal to 0 is the probability of outcome x3. Note that P1 plus P2 plus P3 is equal to 1. Figure 2 shows the representation of a simple lottery in probability simplex. Moving up in this diagram means the likelihood of the first outcome will increase as P1 increases. Similarly, moving down, left and down, right will increase the likelihood of occurrence of the second and third outcomes respectively. The above example of lotteries can be generalized to n number of outcomes where the sum of their probabilities of occurrence is 1. Next is compound lottery. Suppose there are two lotteries, say P star and P double star. The convex combination these two lotteries is also a lottery. A convex combination of lotteries is known as compound lottery. In other words, a compound lottery is a lottery of lotteries. It is a type of lottery whose prize is itself a lottery. Given S simple lotteries with probability ai, where I is equal to 1 till S attached to each simple lottery, then the compound lottery can be denoted as Ls is equal to Ls till Ls A1 till As, where As is greater or equal to 0 and summation 1 till S As is equal to 1. As you can see in figure 3, it is the representation of a compound lottery. We can also represent the compound lottery as a vector in a probability simplex. Suppose there are two lotteries P star and P double star. The lottery P star occurs with a probability of alpha and the lottery double P star occurs with a probability of 1 minus alpha. Then the compound lottery can be represented as follows. C is equal to alpha into P star plus 1 minus alpha into double P star. In figure 4 you can see it is the representation of a compound lottery in probability simplex. Next is reduced lottery. A simple lottery which is obtained from a compound lottery is known as a reduced lottery. A reduced lottery R can be obtained by using the following formula. R is equal to A1 into L1 plus till As into Ls. As you can see in figure 5, it is a representation of a reduced lottery and you can see their outcome. Outcome 1 is equal to 1 upon 3 into 3 upon 9 plus 2 upon 3 into 2 upon 6 is equal to 9 upon 27. In a similar fashion, outcome 2 is equal to 1 upon 3 into 4 upon 9 plus 2 upon 3 into 3 upon 6 which is equal to 13 upon 27. Similarly, outcome 3 is equal to 1 upon 3 into 2 upon 9 plus 2 upon 3 into 1 upon 6 which is equal to 5 upon 27. We can also represent the reduced lottery in a probability simplex. Suppose there is a compound lottery, say C star, given as follows. In the given figure 6, you can see reduced lottery. The above reduced lottery can be represented in probability simplex as follows. Figure 7 is the representation of a reduced lottery in probability simplex. Now we will discuss about preference axioms. There is a possibility that two or more compound lotteries will produce the same reduced lottery. In such a situation, a person would be indifferent between the two or more compound lotteries. There is a hypothesis known as consequentialist hypothesis which says only the consequence and probabilities attached to it matter and not the way that is followed in order to obtain the consequence. Therefore, we assume that a decision maker who is rational will only care about the consequences and not about the way in which they are achieved. So, a rational decision maker will obviously have preferences over a cluster of lotteries. In what follows, we will discuss a set of axioms that such a preference ordering must satisfy. Let L hat be the set of all the simple lotteries and the relation weakly preferred means strict preference over lotteries. It is assumed the rational decision maker's preference weakly preferred is continuous and transitive. Axiom 1. Completeness. If there are any two simple lotteries, say L star and L double star, either L star is strictly preferred to L double star, L star weakly preferred L double star, or L double star is strictly preferred to L star, or both L star is indifferent to L double star, that is the rational decision maker is indifferent between the two lotteries. Axiom 2, transitivity. Suppose there are three lotteries, L star, L double star and L triple star. If the preference are transitive, then L star is weakly preferred over L double star and L double star is weakly preferred over L triple star, which leads to L star is weakly preferred over L triple star. Axiom 3, continuity. A preference relation weakly preferred in lottery space L hat is said to be continuous if for any lotteries L star, L double star and L triple star which belong to L hat such that L star is strictly preferred to L double star and L double star is strictly preferred to L triple star, that is L star weakly preferred over L double star over L triple star. There is some beta which lies between 0 and 1, that is beta belongs to 0 and 1 such that beta L star plus 1 minus beta into L triple star is indifferent to L double star. The continuity axiom implies that if a lottery L star is preferred over another lottery L triple star, then any lottery that is close to the lottery L star will also be preferred over lottery L double star. This axiom can be understood as follows. If there are two simple lotteries and a strict preference relation defined over these two, then a small change in probabilities will not affect the order of preference between these lotteries. We can understand axiom 3 further with the help of a probability simplex diagram. Suppose there are two lotteries L star and L double star where L star is weakly preferred over L double star and there is a neighborhood of L star and of L double star which are donated by N, L star and L into L double star. It follows that L1 star is weakly preferred over L2 double star where L1 star belongs to N L1 star and L2 double star belongs to N L double star. Now figure 8 shows the continuity axiom. Axiom 4, monotonicity. Suppose there are two lotteries L star and L double star. Out of these two lotteries, the one that assigns a higher probability of getting a higher outcome will be preferred. Axiom 5, independence. A preference relation weakly preferred satisfies this axiom. We assume that there are three lotteries L star, L double star and L triple star and there is some beta lying between 0 and 1, that is beta belongs to 0 and 1. Then we have L star is weakly preferred over L double star if beta L star plus 1 minus beta L triple star weakly preferred over beta L double star plus 1 minus beta L triple star. In simple words, these axioms can be explained as follows. Suppose we combine two lotteries with a third lottery. The order of preference over the first two lotteries will not depend on the particular third lottery that is being used. This axiom can be shown with the help of the following probability simplex diagrams. Figure 9 shows the independence axiom. L star weakly preferred over L double star if beta into L star plus 1 minus beta L triple star weakly preferred over beta into L double star plus 1 minus beta L triple star. Figure 10 shows the independence axiom. If the preference relation of a decision maker satisfies the above axiom over a set of simple lotteries L hat, then we can assume that there is a utility function U such that this utility function will represent these preferences. Now we will study about expected utility theorem. Expected utility theorem. An utility function U bracket has an expected utility form if numbers A1, A2, A3 till AT can be assigned to a total number of T outcomes such that for every single lottery L star is equal to P1, P2 till Pt belongs to L hat, we can express U L star is equal to A1 into P1 plus A2 into P2 till AT into Pt. This kind of utility function, which takes the expected utility form, is also known as von Neumann-Morgenstern (VNM), expected utility function. The utility function which we have mentioned above is linear in probabilities. In fact, a utility function will have expected utility form if and only if it is linear in probabilities. Suppose there are a total of T lotteries. For any lottery, Lt belongs to L hat where T is equal to 1, 2, 3 till T. If the following is true, then it is said to be in linear in probabilities, where the probabilities are given by beta 1, beta 2, beta 3 till beta T is greater or equal to 0, and the sum of these probabilities is 1. We can write U summation of T, where the value of T is between 1 till T, beta T into Lt is equal to summation of where T ranges from 1 to T, beta T into ULT. The utility of the expected value of the T lotteries, that is U summation value ranges T is equal to 1 till T, beta T into Lt is equal to the expected utility of T lotteries, that is summation of the value T is equal to 1 till T is equal to into beta T into ULT. Note, this expected utility property is cardinal because the rank and the number assigned by this utility function both matter. Second, the utility function which is in the expected utility form will preserve any positive affine linear transformation. If U bracket and Z bracket are two utility functions representing preference weakly preferred, if U bracket has the expected utility form, then Z bracket will also have the expected utility form if and only it is the positive affine transformation of U bracket. That is, suppose there are numbers A greater than 0 and B such that Z L star is equal to A into UL star plus B, where L star belongs to L hat. Remember, any other transformation except a positive affine transformation of U bracket will not preserve the same preference weakly preferred. Now we will discuss upon the violation of expected utility theorem. There are a number of experiments which violate the independence axiom discussed in section 3.3 above. Among these experiments, there is a famous one by Morris alias 1953. Alias paradox. Suppose there are two situations and three prizes in each situation. The amounts of the prizes are rupees 20, rupees 10 and rupees 0 respectively. The two situations are illustrated below. Situation 1, the prizes are 20, 10 and 0 respectively, and the lotteries and their probabilities. Situation 2, prizes given and the lotteries and their respective probabilities. It is seen that in general, rational people give more value to those things which are sure to happen. Thus, in Alias experiment, majority of the respondents choose lotteries L1 over L2 in situation 1 and L2 dash over L1 dash in situation 2. Therefore, the experimental outcome can be written as follows. The preference in situation 1, L1 is greater than L2. By choosing L1 over the L2, the respondent is 100% sure that he will get rupees 10 as the prize money. But if he tries to choose L2 over L1, then probability attached to winning rupees 20 is only 0.10 and probability of winning rupees 10 is 0.89. Also, he may not get anything at all because the probability of getting prize money rupees 0 is 0.01. So, he will choose L1 over L2. The preference in situation 2, L2 dash is preferred over L1 dash. As we can see in lottery L1 dash, people will get prize of rupees 10 with probability 0.11, and in lottery L2 dash, people will get prize of rupees 20 with probability 0.10. There is not much of difference in the probabilities, and majority of the people have chosen L2 dash over L1 dash. Now consider the following. According to expected utility theorem in situation 1, the following can be written as 0 into U20 plus 1 into U10 plus 0 into U0 is greater than 0.10 into U20 plus 0.89 into U10 plus 0.01 into U0, or 1 into U10 is greater than 0.10 into U20 plus 0.89 into U10. Subtracting 0.89 into U10 from both sides, we get 0.11 into U10 is greater than 0.10 into U20. Clearly, if the above equation holds true, then L1 dash is preferred over L2 dash, but this is a contradiction of the fact that L2 dash is preferred over L1 dash, which was observed via Elias experiments. In this case, theory contradicts what was observed in reality via Elias experiment. So, Maurice Elias 1953 tried to show how the independence axiom gets violated in the real world. Next is Elsberg paradox. Elsberg paradox is based on subjective probability theory. In this experiment, the respondents were informed that a box contains 300 balls, out of which 100 are red and 200 are either blue or green. There are two situations. Situation 1. Choose between L1 and L2. Lottery L1. The person will get rupees 500 if the ball is red. Lottery L2. The person will get rupees 500 if the ball is blue. Situation 2. Choose between L1 dash and L2 dash. Lottery L1 dash. The person will get rupees 500 if the ball is not red. Lottery L2 dash. The person will get rupees 500 if the ball is not blue. It was observed that majority of the respondents choose L1 over L2 in situation 1 and L1 dash over L2 dash in situation 2. This is a very common outcome because in situation 1, it is clear that out of 300 balls, there are 100 red balls, but is not clear exactly how many blue balls are there out of the remaining 200 balls. So, the respondents choose L1 over L2. In situation 2, again the respondents are clear how many balls out of 300 are not red, that is 200, but they did not have a clear idea exactly how many balls are not blue out of 300 balls. So, here the experimental outcome can be written as the preference in situation 1, L1 is preferred over L2. The preference in situation 2, L1 dash is preferred over L2 dash. But this kind of preference violates subjective probability theory. Let us see how this happens. First, we define the events R, B, R star and B star as follows. The ball is red R, the ball is blue B, the ball is not red R star, the ball is not blue B star. According to basic axioms of probability, we know P R is equal to 1 minus P R star, P B is equal to 1 minus P B star. In light of this, now consider the experimental outcomes that were observed. In situation 1, we have L1 is preferred over L2, so PR into U500 is greater than PB into U500, which gives PR is greater than PB. In situation 2, we have L1 dash is preferred over L2 dash, so PR star into U 500 is greater than PB star into U 500, which gives PR star is greater than PB star. Studying equation 1, equation 2 and equation 3, we can easily make out that they are inconsistent. The Elsberg paradox seems to hold true because people in this experiment tend to think that betting for or against R, red, is safer than betting for or against B, blue. Now we will discuss about risk aversion. Now let us consider the outcome of the lotteries in monetary terms. That is, now we will say that the prices associated with the lotteries are in monetary form. We can assume here, if the decision maker's preferences satisfy axiom 1 to 5 discussed in section 3.3 above, then we can make use of an expected utility function to represent his preferences over the lotteries. This way, we can figure out the decision maker's action over the money gambles using the expected utility function. To calculate the expected utility for a money gamble, we can make use of the following formula. E L star is equal to P Ux plus 1 minus P Uy, where X is the prize money which a person gets with probability P and Y is the prize money he gets with the probability 1 minus P. Let's use an example to understand the attitude of people towards risk. Note that risk refers to a situation where there is more than a single possible outcome of a decision and the probability of each possible outcome is given or can be estimated. Consider a gamble that gives me rupees 200 with probability half and rupees 0 with probability half. And there is another offer which gives me a sure amount of rupees A. Now the question is whether I should accept the second offer, which is certain, or I should play the gamble. The expected value which I get by playing the gamble is EV is equal to half into 200 plus half into 0, which makes out rupees 100. If I do not want to take the risk, then I will accept rupees A, which is somewhat close to rupees 100, but is strictly lower than it. Suppose rupees A is equals to rupees 80, then in this case, my expected utility from the lottery is less than the utility of the expected value of the gamble. This means I would prefer a given sum of money with certainty to a risky asset with a slightly higher expected value. Here, rupees 80, which is minimum amount which I will accept for not playing the gamble, is known as the certainty equivalent. It equals the certain amount of money that offers the same utility as the lottery. We use this concept to define risk premium as follows. Risk premium is equal to expected value of the lottery less certainty equivalent. Here, the risk premium is rupees 20. This much amount I can pay to someone else to take the risk for me. This is the maximum amount that I am willing to pay to avoid the risk. There are three types of decision makers depending upon their behavior towards risk. Consider the following example. Suppose a person has to choose either one of the following two situations. Situation 1, get rupees 100 with certainty. Situation 2, get a lottery which yields rupees 50 with expected probability half and rupees 150 with probability half, so that the expected value of the lottery is rupees 100, since 100 is equal to half into 50 plus half into 150. A risk-averse person will prefer situation 1 to situation 2. A risk-loving person will prefer situation 2 to situation 1, while a risk-neutral person will be indifferent between the two situations. In what follows, we discuss the differences between risk-averse, risk-loving and risk-neutral agents in more detail. First, risk-averse. If the expected utility of any lottery L star Pux plus 1 minus Puy is not more than the utility of getting the expected value Upx plus 1 minus Py of the lottery for sure, then we can say that the decision maker is a risk-averse person. If the decision maker is risk-averse, then u px plus 1 minus py is greater or equal to pux plus 1 minus puy. If greater or equal to is replaced by strict inequality, that is greater, then we can say the decision maker is strictly risk averse. A risk averse person has a concave utility function. The more concave the curve, the more the person will avoid risk. Second, risk lover. The decision maker is a risk loving person if the expected utility of any lottery is more than the utility of getting the expected value of the lottery with certainty. If the decision maker is a risk lover, then figure 12 shows risk lover. If less than or equal to is replaced by a strict inequality, that is less than, then we can say the decision maker is strictly a risk lover. A risk lover person has a convex utility function. The more convex the curve is, the more the person will love to take risk. Third, risk neutral. A decision maker is said to be risk neutral if the expected utility of any lottery is the same as the utility of getting the expected value of the lottery for sure. Figure 13 shows risk neutral. If the decision maker is risk neutral, then u px plus 1 minus p into y is equal to pux plus 1 minus puy. Measuring risk aversion. The most commonly used method to measure absolute risk aversion was developed by the economists Arrow and Pratt. It is as follows. Our aversion x is equal to minus u double dash x upon u dash x, where x is equal to consumer current wealth. Note, if our aversion x is greater than 0, then the person is a risk averse person. If our aversion x is equal to 0, then the person is a risk neutral person. If our aversion x is less than 0, then the person is a risk lover person. We can deduce that the risk aversion of a person can change with a change in his wealth, as our aversion is a function of wealth x. The following examples demonstrates the above. Example 1. If the utility function has a quadratic form such as ux is equal to c plus dx square plus ex, where d is less than 0 and e is greater than 0, our aversion x is equal to minus u double dash x upon u dash x is equal to minus 2d upon 2dx plus e less than 0. In this case, risk aversion increases with an increase in x. Example 2. If the utility function has a logarithmic form such as ux is equal to log of x, where x is greater than 0, our aversion x is equal to minus u double dash x upon u dash x is equal to 1 upon x greater than 0. In this case, risk aversion decreases with an increase in x. Example 3. If the utility function has an exponential form such as ux is equal to negative e minus alpha x, where alpha is greater than 0, our aversion x is equal to minus u double dash x upon u dash x is equal to alpha. In this case, risk aversion is not affected with a change in x. The formula given by Arrow-Pratt is used to calculate only absolute risk aversion. It is used to measure how a person thinks about lotteries, whose prices are defined in terms of an absolute monetary value. There can be gambles that offer to increase or decrease your wealth by a certain percentage and are known to be relative lotteries. Its prices are defined relative to the current wealth of a person. So, relative risk aversion can be measured by our aversion x is equal to x into our aversion x is equal to minus x u double dash x upon u dash x. Summary. Under certain preference axioms, the expected utility theorem is a useful tool to express the utility of a decision maker under certain situations. The independence axiom is an important axiom for the expected utility theorem. If this gets violated, then the expected utility theorem may not work efficiently. The concept of risk aversion can be applied to many situations. It helps in starting attitude towards insurance, as the decision of a person changes with the change in his attitude towards risk.